Nadine, sorry. Last week we were talking about, we were doing this problem where we had to calculate the work done by each and every force acting on this box. It's great. And I would like us to finish it. Okay, we found the work done by each and every force. We found that the force of friction does a negative work of minus 625 joules. The weight and the normal force do zero work because they act at an angle to the displacement of 90 degrees. And then we had the tensional force, this 50 Newton tensional force that acts at an angle of 30 degrees with a horizontal. And this force was doing this work, 1082.5 joules. The thing is now that we need to calculate the net work done on the trunk. When we say the net work done on the trunk, we mean the work done by all forces acting on the trunk, which means we have to add all these works. So the net work, we have spare space here. So the net work, and we can symbolize it by work net, is the sum of all, the algebraic sum of all these works, because work is a scalar, so we add their values, all these values algebraically. So we have minus 625 joules from the frictional force, plus zero from the weight and the normal force, and then the tensional force does a positive work, and this is 1082 joules. And if we add all these values, remember this is a negative number, we'll end up with a net work done, which is, according to my calculations, 457.5 joules. So that would be the net work done on the grate. So very often it's important to know the net work done on an object, because in any case it's the net work done that either gives the object energy to move faster, or it takes away energy from the object. So the net work from all the forces. So this is the easiest way to find the net work done on an object. We could find the net work done in a different way, by first finding the net force acting on the object, and then the net work done would be the work done by the net force. So in other words, the net work done in this second way of finding would be the net force times the displacement that the object moved. And of course, if there is an angle between the net force and the displacement, we should also say cos of this angle theta. So this is another way of finding the net work done on an object. And it must be said, this is a little bit more complicated because we have to find the net force. And to find the net force, we have to add all the forces as vectors, because forces are vectors. And it has more work. So, but nevertheless, it's a second way of finding the net work done. And let me ask you something. Do you want us to do this second method of finding the net work by finding the net force acting on the object? Because it's good to know this way. I don't know how easy you find to add all the forces. So yes or no? You want us to find the net work done from the work done by the net force? Yeah, okay, good. That was the correct answer. Very good. All right, so so then to find the net work done, remember, we need to find the net force first. So this is what we're going to do now. Now, because the diagram is not there anymore and we need it, let me draw it again here. So we have, I'll draw a small one. Here's the box, and there is a weight which is, do we know the weight? I don't remember now. We know the mass. It's 20 kilograms. The mass is 20 kilograms. So we can find the weight. This will be mg. Then we have a normal force, which I have no idea what it is. Okay, we'll read the problem again. Then we have this tensional force that acts at this angle of 30 degrees, this force. F. And this is 50 newtons given. And this angle is given is 30 degrees. And we know the displacement, which is, we call it D, how much is that? 25 meters. What else? There is a frictional force of friction, which is 25 newtons. This is 25 newtons. Okay, remember this is, we know that. To make it easier, let's say that the G, let's take it as 10 instead of 9.8. So that if it's 10, this will be 20 kilograms times 10, it's 200 newtons, just to have round numbers. All right. Okay, so what does this say? A man pulls a 20-kilogram trunk 25 meters along the floor by exerting a constant force of 50 newtons. Acting at an angle of 30 degrees to the horizontal, the frictional force exerted by the floor on the trunk is 25 newtons. Do we have enough information to find all the forces? I'm worried about the normal force. We don't have this value, and maybe not. Anyway, we have to devise values here. Okay, let us assume that this object moves at constant velocity, and the reason why we assume that is because we don't know the value of the normal force. We don't know the coefficients of friction here, but if we know that this object moves at constant velocity along the floor, then we know that the forces are at equilibrium, so we can find this normal force. So how much would this normal force be? Okay, so at equilibrium, remember now, it means that the object moves to the right at constant velocity. All right, so on the y-axis, what do we have on the y-axis? It means the vertical level. We have the weight acting downwards, we have the normal force acting upwards, but we must not forget that this tensional force has a y component as well. So there would be another force, let's call it Fy, to be the y component of the tensional force. We can find it. So anyway, so all the forces acting on the y-axis are the normal force, not N, F. We have the normal force, which we call Fn, plus the y component of the tensional force, which we call Fy, and this must equal all the downward forces, which is just the weight in this case, which is mg. All right. From there now, because we know this and this, we can find this normal force. Okay. So from there, the normal force is mg minus Fy. The mg is 20 times. Okay, we said we'll take it as 200 newtons minus the Fy. The Fy now is 50 newtons sine 30. 50 newtons times the sine, the 30-degree angle. You see why? Because this Fy is equal to this length, which is opposite the angle 30. So it is associated with the sine of the angle 30. So it's 50 times sine 30. All right, so let's see now what is happening here. What is this? Minus 50. Okay, 50 sine 30. What can this be? Oh, sine 30 is 0.5, isn't it? So this should be, all this should be 25 newtons, which means this normal force must be 175 newtons, and I hope my calculations are correct. Okay, so this is the value of the normal force. Okay. In any case, if we assume that the system is at equilibrium, there's no net force on the y-axis. There's no net force on the y-axis, so it was not even necessary to do the calculations. In other words, the net force on the y-axis is 0. Now on the x-axis, you know something that, yeah, I shouldn't have said that the object moves at constant velocity, because actually we don't need it. We don't need it, and also we can see from the values here that these two forces, the x component of the tensional force and the friction, are not equal and opposite. What is the x component of the tensional force? Is Fx. It is 50 newtons times the cosine of the angle 30 degrees, and how much is that? 50 times the cosine of 30 degrees, because the cosine is 0.866, so that should be 43.3 newtons. You see, 43.3 newtons is bigger than the 25 newtons, which means the object moves to the right and accelerates, actually. All this nonsense that I said before, please forget them. It was, yeah, I panicked because we didn't know the normal force, but we don't really need it. Okay. So, all right, so we have the, so let's see now what's happening on the x-axis, because on the x-axis we see we have one force, this x component of the tensional force, which is 43.3 newtons, and on the left-hand side we have the frictional force, which is 25 newtons. We see we have a net force along the x-axis, which is the net force on the x-axis is, if I subtract the two, 43.3 newtons minus the 25 newtons, which is the friction. And what is the result here? Let's do the calculation. For 43.3 minus 25, that should be 18.3. This is 18.3 newtons. This is a normal force, the net force acting on the x-axis, and in fact this is generally the net force acting on the block, because the net force acting on the y-axis must be 0. The block does not move up or down, so this net force is 0. So the net force acting on the object is 18.3 newtons. This is the net force. And the net work done by the net force is the work done by this force. So the net work done now, because we started discussing how we're going to find the net work done using the net force, is the net force acting on the block times the displacement of the block, which is this distance of 25 meters in this direction. So times d, the angle between the displacement d and the net force is 0, because remember this net force is actually it's acting along the x-axis. It's not the effect. It's the net force along the x-axis. So it's a force that acts in this direction. How can we call it? I don't want to call it, to give it the same name as the x component of the tensional force. Let's call it F1. No, F net. F net along the x-axis. Let's call it, let's give it this name. So the net force on the object is the net force that acts along the x-axis, and the displacement is in the same direction. If you look there, here's the displacement. So both the net force and the displacement act in the same direction, which means the angle between the two is 0. So if we add here times cos of 0 degrees, this is actually 1. Okay, so this is equal to F net times the displacement. And now if we do the calculation, if we add the values and we do the calculation, we should find the same network as we found with the previous method. So F net is what is 18,3 newtons times D, which is 25 meters. 25 meters, and this is now, we're going to find the same value. All right, 18,3 times 25, and this is 457,5. Okay, all right. Oh, and there it is. We find the exact same value that we found with the previous method, where we just had to add the work done by each and every force algebraically. You see, that is the work we done by adding the works. And here is the same value that we found for the work done, the net work done, by adding first all the forces to find the net force, and then taking the net work done as the work done by the net force, moving the object at least in this displacement, and there we have it. So, all right. So, sorry, Nadine, did I confuse you? Because I did confuse the beginning. Yeah. Nadine, is there any place here where I must repeat? Oh, good. So that means that you are familiar, I mean, you are feeling comfortable finding the net force on X and Y directions to find the total net force from the forces acting on an object, I hope. Okay. Okay, let's share again. You know now what I want us to discuss, a very important case which concerns the work done by an object that moves, that changes elevation from one level to another. Like we have this block here. Let's say that this line here represents the ground, okay, the ground. Like we can take this to be our 0 elevation. And we lift this block up to some higher elevation. You see, here it's actually 1, 2, 3, 4 cases, 4 scenarios, A, B, C, and D, where the block is lifted to this higher elevation, which is up there, the height h, but by following different paths. You see, in the first diagram, a force F lifts the block vertically up. You see, in the other 3 diagrams, though, the block is lifted from the ground up to this elevation through different paths. Here, it follows this path. Here we have this path which is longer than this path, which means this angle theta is less than this angle theta. And finally, in this scenario, the block is moved from the ground to this elevation following this longer path, which makes an even smaller angle with the horizontal. So I want you to see that these angles are not the same. And also I want you to see that these displacements for moving the block from the ground to the new elevation are different. And what we need to see here is that in all those cases, we do the same work. in lifting the block from the ground to this new elevation, no matter which path we follow to lift it from the ground up to this new height, as long as this height is the same for all of these scenarios, which sounds very strange, but this is very important. The work done to move an object from the ground to an elevation h is always the same, no matter which path we follow. So this is what we need to prove here. Why is the work done the same in all these cases, in all these scenarios? And in fact, the work done in all these cases is equal to this force F that we apply on the object times this vertical elevation h. So it does not depend on the path taken. So we're going to show why all these works equal to this work. So, okay, if we look at the first scenario, this is nothing difficult because we see that the force F acts vertically up, and we see that the displacement is also vertically up. And this, in this case, what is the displacement is from there up to there. This is the displacement. We can call it h because it has the name h already. So what would be the work in this case? Would be F times h times the cosine of 0 degrees, which is 1. Okay. So already we see that in this case, the work is equals F times h. But now let us see another of these scenarios. Let's take this scenario. All these scenarios are exactly the same, just the elevations, I mean the path taken. These d's are different and the angle theta is different. Now, if we apply normally what we know about work done, what is work done in general? Is work done in general is the force times the displacement times the cosine of the angle phi between those two vectors, isn't it? Be careful. What is this angle phi? Is the angle that these two vectors form. For example, if the force F acts at an angle with a displacement d, this is the angle that we're talking about, phi. Okay. So if we apply this general formula to our scenario, be careful. Let us find the force and the displacement. Look at the force. It's this F. Now the displacement is this blue arrow here, which we call d. So in our case, the work done is the force, this force F times the displacement, which we call d, times the angle between those two vectors. Be careful, the angle between those two vectors is this angle, not this angle. Okay, so let's call this angle phi. So times the cosine of this angle phi. I hope this is very clear to you. So here is the angle between the two vectors that we are concerned. Now, what is this angle phi? We don't have this phi, but we know we have the theta. The theta, we consider it as a given, okay? Because it's shown on the diagram. So, but look at this phi. This phi, I mean from the geometry, look at this, this force F, if we extend it, is perpendicular to the ground, isn't it? If this is the ground, here is the ground. So this angle is actually 90 degrees, isn't it? And this is the angle theta, which means the angle phi, we can write it as 90 degrees minus theta. Okay, this is 90 degrees minus theta. So this unknown angle, we can write it as, okay, this stays the same, cosine of, that will be 90 degrees minus theta. I hope your trigonometry is good. All right, but the cosine of 90 degrees minus theta, this is actually this is equal to the sine of the angle theta. Okay, so we see that F times D is, sorry, the work done by the force F is F times D times sine of the angle theta. But now, D sine theta, if we look at this diagram again, let me make a clear diagram here of this. I want to draw this triangle. We have, this height is h, this is the angle theta, this is the displacement d. Now, if you look at, if we take the trigonometric, from the trigonometric functions, this height h, is actually the hypotenuse d times the sine of this angle theta, isn't it? I mean, we have applied this many times. So if you look now here, d sine theta, this d sine theta, it's actually the h. This is what we found from the trigonometry of this right angle triangle. So you see that, what did we find finally? That the work done in this case is F, the force F times h, which is the same as it was here when we moved the block straight away up from the ground to this level. So we found again the same formula. And of course, we could do the same in this scenario and in this scenario, because in all those cases, the d sine theta is always equal to the h, the same height. So in all those cases, the work done is always F times h. And here, the work done is similarly F times h, much as it's here, F h in there. So in all cases, we see that it doesn't matter at all what was the length of this displacement. What matters is what this height is and the force that we apply on the block. So this is a very, very important conclusion, and it's going to be very helpful in different problems. When we have an object whatever, of mass m, whatever, and we move it from some level to some other level, the only thing that matters in how much work we do is this vertical height h, and then the work done by any force acting vertically on this object, the work done will be always F times h, no matter if we take this way or whatever way we take to get it up there. From the moment that we take it from the same level to the same level, the only thing that matters on how much work we do is this vertical elevation. Okay, provided of course that we use the same force in all cases. So this is something, a very important aspect of the work done in moving an object inside the gravitational field.